Okay, so before we look at some properties of indefinite integrals, things we can do with them to make it a little easier to do, let's just consider a basic example. So what we do here is we say, okay, I got the indefinite integral of x to the third dx. The dx on there is kind of like in derivatives, it's indicating which variable in derivatives we're differentiating with. Now it's kind of indicating which variable we're integrating with respect to. So we said we need an antiderivative. Well, by our power rule, so we just have to add 1 to the exponent and divide by it. So we do just that. And of course, adding 1 to the exponent would make it 4. Dividing by it would make it 1/4. Now we want not just an antiderivative, though, we want the whole family of antiderivatives. So we say plus c. Add a constant plus c. Okay, so now we're going to look at some properties of antiderivatives. We'll talk about those a little bit. And we're going to see that they're related to some of our properties for derivatives. So we pick some real number a. Oops, I'm sorry. Apologize for that. Program got a little out of whack here. So we let a be a real number. We take any two functions, f and g, just functions that have antiderivatives over some common interval. So then we take any function, integral of a constant times a function. Turns out all we have to do is factor that constant out. So the integral of a f of x dx is just going to be a times the integral of f of x dx. Much like you can take a constant out of a derivative, because antiderivatives is just reversing that process, we can also factor a constant out for that. So now, if we have the, excuse me one second, apologize there for the interruption. So here we have an integral of a function, sum of two functions, f and g, or a difference. And much like you do with derivatives, it turns out, well, hey, we can do the exact same thing with antiderivatives. We can distribute the operation, or the indefinite integral, over a sum or a difference. And so we just do the antiderivative of each piece, or the indefinite integral of each piece. So now we're ready to look at some examples of finding some antiderivatives. So first we have the integral of 3x to the fourth. Excuse me again. Oh, there you go. You got something for free, singing of Frozen or something like that. Anyway, back to the problem. We have the integral of 3x to the fourth dx. We can take that constant, 3, and factor it out. And then we have the integral of x to the fourth dx. And then we just apply our power rule. Power rule says, hey, add 1 to the exponent. Well, if you add 1 to 4, it'll be 5, and then divide by it. So we get the result 3 times 1/5. Don't forget to plus a constant. And then finally, we get 3/5 x to the fifth plus a constant. Okay. So the constant can just be factored out, much like it can be in a derivative. So let's consider secant squared dt. Now, this one's a little bit different. Secant squared, this doesn't have any addition, doesn't have any subtraction, doesn't have a constant being multiplied. Now it is secant times secant. Well, unfortunately, thinking in terms of multiplication, I didn't give any properties for multiplication. And that's because you're actually going to have to wait to a Calculus 2 course where you discuss something called integration by parts to talk about a product of two functions. But fortunately for us, that's okay, because here it's okay because we know that secant squared is the derivative of something. Specifically, we know it's the derivative of the tangent function. Okay, so here we just recognize that as the antiderivative, or as the derivative of the tangent, so the tangent would be its antiderivative. Interestingly, right now, if that was a secant, just secant t dt, you'd be like, how do I do that? Well, it'd be kind of hard. We'll actually learn a little later on how to handle that, but for now, it's actually easier to do what seems to be a more complicated problem. So now we move on to our next example. Now at first glance, this example seems a lot more complicated. Just said a moment ago we can't do multiplication of things. Well, we really can't do division either. But just like in derivatives, we can, I'll say it again, we can make use of algebra to rewrite something. And that's exactly what we're going to do here. So what I've done is I've taken that x squared and I've divided that into each thing in the numerator. So it's a single denominator, so I can distribute it through each thing in the numerator. So I have 8x cubed over x squared would be 8x. 9x squared over x squared would just be 9. And then 6 over x squared would just be minus 6x to the negative second dx. Now what I'm really going to be using here are several of my properties that will allow me to break up this sum and difference of things into a group of separate integrals, and also factor out any constants that I don't need. So I start with doing that. So I can have 8x by itself, but I can also factor out the 8. So I get 8x dx, and then plus the integral of 9 dx, and then minus 6x to the negative second dx. Now the first one of these is straightforward, the 8x dx. We just add 1 to the exponent. So 1 to 1 would be x squared, and then divide by it. So we get 8 times 1/2 x squared. Now we haven't talked about an example like this yet with the integral of a number, but what function would you differentiate to just get 9? So well, the only thing I can think about would be, can't be a number, because if I differentiate a number I get 0. Wouldn't that just be 9x? And then finally for the last one, minus 6 times, and then the integral of x to the negative second. We'd add 1 to the exponent, which would be negative 1, and then divide by it. And then don't forget, each one of these actually had their own constant, but if you had a constant plus constant plus constant, that's just one more constant. Okay, just one more constant. So we write the constant down only the one time. Now it's just a matter of going through and doing a little bit of cleaning. 8 and 1/2 would be 4x squared plus 9x, and then the two negatives make that plus 6, and then it's x to the negative 1, so it'll be over x. It'll be over x. And so those are some examples of doing some antiderivatives, using the various properties, or using rules and things that we already know about with derivatives, so that we can now do antiderivatives, or, as we're doing here, definite integrals, which is, again, a family of antiderivatives. Okay, so in the next video, we're going to talk about something called differential equations, and so we'll get to that in a moment.